Hi, I'm Sriraam. I'm an associate professor at informatics. So what we are looking at are basically machine learning models, probabilistic models from large-scale databases, what we call as real data than tabular data. So it's collaborators all over the world, and we have a fantastic lab of 8 PhD students and undergraduate student Alex, whom I'm trying to convert to a PhD. So it's working. So really, what we are interested in is broadly, we refer to this field as statistical relational AI, because the way we see it, the data is multi-relational. It's stored in tables, no longer on single files anymore. So it's nicely organized in tables, extremely noisy. So I once worked with electronic health records, and so the data that they provided with me had one medication that was prescribed by the physician. A slightly different dosage was actually administered to the patient. A different one was recorded on the by the nurse. And finally, because the insurance will not pay for it, the pharmacy billed a different medicine. So for one particular medicine, we had 4 different entries that we have to somehow consolidate when making these decisions. So the way we do it is we use a higher order logic to represent the data, which is naturally multi-relational. We use probabilistic models. And then the idea for us is putting both together. So our method, and I just gave this talk 2 days back in London, and I was talking, the left side is the European view, because they worked a lot on these knowledge representation problems for the last 50 years. The right is more the US and Canada view, because we have made a lot of progress quickly in machine learning, and now we are figuring out, now that we have these machine learning algorithms, how can we handle multi-relational data? So this is the field of statistical relational AI, and we've been working on basically 2 types of problems, the learning problem and the inference problem. Learning problem is where you have no model, somebody just gives you data and some expert input, and we are able to induce these models. And we kind of do this large-scale learning, and because everything is deep nowadays, we also jumped into the deep bandwagon, and we're doing relational deep models. And then there is this problem of inference, where I know the model, and then I'm giving a new situation, what should I do? So if I've learned a model, I see some new data point, new situation, what should we do? So we do a bunch of tasks in this space as well. So in doing so, we have this notion of having a human in the loop. And if you think about how humans have been involved so far in machine learning, so on the left side are the case where only examples are being provided. The human is treated as a mere labeler. The human is there to provide the data set. On the right side is the full expert system view, where the human develops everything that you need. And all you do is just chunk numbers and output the results. So where we work is essentially somewhere in the middle. As I said, on the left are mere labeler, and then somewhere in the middle you have these what are called expectation maximization methods, and on the right is where the human is treated as pure oracle. Where we are is somewhere in the middle. So in our view, the human can provide more. A physician can not just label examples for me, but can explain why he or she did a particular treatment for a particular patient. And or in the case of finance, why did you invest in the stock market? What made you decide to do this? Or simply speaking, why did you not stop at a stop sign? Okay, you can answer these questions. And what we are trying to do is ask the human to provide more input than just give us labels. So can you explain why you did what you did? And we kind of take it, roll it into the model, and somehow learn with it. We've been doing this also in the context of decision theory, where we've been looking at sequential decision making in richer domains. And also this field is of probabilistic model is called inside machine learning as uncertainty in AI. And we have a bunch of papers in this direction. So whenever I hire a student, I tell the student, you basically have 2 components to your thesis. You got to make fundamental contributions to the algorithms. And those are this page right here. The next page talks about the applications that you have to adapt these algorithms on. Because as machine learning practitioners, you know that you take an algorithm, you apply it on any application, it fails all the time. So you got to get it to work. To get it to work, you have to adapt the particular nuances of the learning algorithm to that of the application. So we've been working on a bunch of problems ourselves. We work on navigation of drones. My key focus in the last 5-6 years has been on electronic health records, clinical study data, imaging data, particularly looking at Alzheimer's and predicting who is going to have Alzheimer's, not just who has Alzheimer's at this point. And then we kind of look at other relational things, like we want to understand a machine learning paper. So think of making a bot do a PhD, finish a PhD. So that's the other problem that we are trying to do, is can we make a bot learn what is out there? So essentially build a system where, tomorrow David Crandall's student comes in and says, I want to do deep learning for vision. What is the latest out there? Google just lists the top lists, and I mean top 10 hits. But we want to basically say, no, here is how it has evolved, and here is the last set of papers that was published in 2 conferences back. Okay, and we've been working on natural language processing to do this as well. So that's me. My email, unfortunately, is in blue. Thanks.